Hey class, this is Mr. Roberts at Shasta High School, and we're going to try and take a stab at doing some new topics today. Start kicking off Chapter 9. Today we want to introduce this idea of inequalities, and I don't think it's something that's entirely new to us, but we've used this symbol an awful lot this school year. And every single time we use it, we're basically stating that two things are equivalent to each other. And we've looked at situations where we can write down things that are sometimes always or never true. So for example, if I was to write this, right, this is never true. And if I'm solving an equation, right, and I get a statement like that from the equation I'm solving, I know that there's no solution to that particular equation. Another thing that can happen is I could be solving something and I could get something like this, for example. I could get this 3 is equal to 3. So for example, if I had the equation, I'd say like 3x plus 3 equals x plus 3 plus 2x. When I solve that, I can see on each side I've got 3 factors of x. Here's 3 factors of x. And if I choose to take those away, I'm left with, hey, 3 is 3. What this means is that the thing on the left and the right-hand side are identities, and it doesn't matter what I pick for x, I'm always going to get the exact same value. So x can be anything, and this equation is going to be true. And then up here, there could be an equation where, for example, I could have x plus 3 equals 2 plus x plus 3. Well, if I take away the x from both sides, right, this becomes 3 is equal to 2 plus 3, 5, right? And we would say there's no solution there. So we've kind of seen this. Things are sometimes true, they're always true, or they're never true. This is a never true situation. This is this isn't always true. Doesn't matter what I pick for x. But more often than not, we're looking at situations where I ask you to solve an equation equals x. That's a bad, well, I'll just say x plus 7. Okay. So what's x here? Well, let's see. The particular value of x will make this true, right? If this thing has to be the same as that, the value of x that would make that true would be, well, 2x plus 5 is 7. So 2x is 2, so x is 1. Oh, yeah, I can see it now. So if I put 1 in for this x and 1 in here, 3 times 1 is 3 plus 5, this becomes 8. And then 1 plus 7 becomes 8. So in the case that x is 1, right? See, this is sometimes true. It's true when x is 1. I could pick a lot of values for x. In fact, just pretty much any number I could think of except for x is 1, and this would not be true. So we've dealt with this symbol quite a bit. What we're going to do today is we're going to start talking about a little bit more robust notation, right? We want to look at more than just that particular symbol. And the symbols that we want to look at are symbols like, can I move over here more? Maybe. There we go. Symbols like, clearly we've seen this one. But let's say this, right? This symbol right here. This symbol. Now you've seen it written down before, and I think most of you know that this means less than, right? This symbol means greater than. This symbol is two things. Well, it's an or that joins them. It's either less than or equal to. And then this one goes the other direction. This is greater than or equal to. So when we see these symbols inside of what we used to call an equation, right? If I saw this symbol inside of what we were calling an equation, it changes it. It's no longer an equation. It's an inequality. And we're saying that two things are not equal to each other. But more specifically, we're saying how they're not equal. So for example, I could say 5 is less than 7. I could say 10 is greater than 2. With numbers, it's kind of difficult to show where this comes into. So we're going to look at these with solutions and how we graph those on number lines. But that's kind of a first crack at this. So in the last couple of homework assignments in Chapter 8, you probably noticed that there were some questions that were bizarre. They would ask you to solve this and graph the solution. And if you were solving something as trivial as, 3x plus 1 equals 7, okay, 3x plus 1 is 7, therefore 3x is 6, and x is 2. Okay, graph the solution. What's that mean? All it means is there's a point on the number line that's represented by that, right? And it's right here. And I would just place a dot right here, 2. So what this is saying, x is 2. On all the numbers on the number line, the one spot, right, that satisfies, that makes this truly true, makes the left-hand side and the right-hand side the same, is the spot when x is 2. And that's what we were talking about when we saw those. So now let's take a look at a couple different inequalities. We're going to kind of do this in reverse, and then we'll do it forwards, and then we'll get to solving some actual inequalities. But let's take a look at a couple graphs of inequalities and see if we can't figure out what they say. So this is the first one I'll bring over here. So I've got this, and you can see that the number 1 is important, right? In fact, that's a pivotal point. The entire universe, if you will, hinges upon this point, x is 1. So what we would do is we would say that there's clearly a 1 here, and then we talk about, okay, so there's the 1, right? That's the pivotal center of the universe, if you will. So what kind of things do I have here? Do I have the things that are bigger than that, or do I have the things that are less than that? Because see, I want to talk about x. I want to talk about values x, and I want to relate them to 1. And this, what I've got graphed here, is this is saying, look, x can be the number 1, right? It can be equal to number 1, just like above, right? Up here, x was 2. But it's a little bit more special than that. Not only can x be the number 1, but it can be any of these values, right? Any of these values down to this side of it. So I can highlight all of these this direction. All of these values of x work. So we would say that x is not just that it can be 1. We can say x is anything that's less than or equal to the number 1. Right, so x is less than or equal to 1. Let's look at another one real quick. Whoops, I don't want to drag that. I want to drag this picture over. And I can't drag the picture over. No, can't drag the picture over. Okay, there's the picture. So you can see now the point that I care about is the number 5. And we're talking about the variable x, right? And this time, you can see x can be 5, right? But also x can be anything that's greater than 5. So I would say here x's are greater than, they're more than, or they're equal to 5. So x could be, for example, it could be 6, it could be 6 1/4, it could be 7, it could be 12, it could be 52, it could be 5. X can be 5 or anything greater than 5. X's are greater than or equal to 5. Now this one's a little bit different. If you'll notice now, my boundary point is not a solid dot, and that changes things slightly, right? So x is, it's not including that point. I still care about talking about the variable x, and I care about this number 2 because that's kind of the center of where everything's happening. But in this case, I would say, hey, x can't be 2 because it's an open dot here. So this is x can be anything that's greater than 2, but not 2 itself, right? So x could be, that's not 2. This is 2 over here, Mr. Roberts. We're talking about negative 2. So x could be, for example, negative 1.5, right? Right in here somewhere is negative 1.5. X could be negative 1/2, which is somewhere in here. X could be 0, right? X could be any of these values going this direction, but x cannot be the number negative 2 itself, and it can't be anything below 2, right? So this is just x's are strictly greater than negative 2. And I'll finish with this one then. So again, my boundary condition, my boundary location is the number negative 2. So I'm going to go ahead and write the negative 2 here, and we're talking about x's. But this time, still, x cannot be that boundary point, right? It's not including it, so I'm not going to say x can be equal to negative 2, but clearly x can be anything that's less than negative 2. So -3, -4, -5, those are all numbers that are smaller than -2. So anything this direction is a solution, but let's not say -2 is, because it's not. So that's how those graphs work. And if I imagine that if I was to come back up and say, oh, okay, so now let's see if we can graph an actual inequality. If I was to come in here and say, well, okay, let's look at this. Let's look at this. What if I've got, I'll use this nice green pen. I'll say x is greater than or equal to 3. Okay, okay. Or let's do this one in orange. X is less than the number 7. Okay, and I'll do one more in blue. X is less than -4. Okay, so let's graph those separately. So first one, x's are greater than or equal to -3. Well, because it has the or equal to tagged onto it, when I go to my boundary point 3, I'm not putting an open dot, I'm filling this dot in, indicating that that point is part of my solution. And it's not just that point, but it's everything, oops, not less than, everything bigger than that, right? X's are all those things that are greater than the boundary condition. X's are greater than or equal to 3. The other one says x's are less than 7. So I'll just do this one. You know what I'll do this. I'll just take this and I'll just slide this down. And now I'll do the orange one in here. So now we're going to say for this, we're going to say x's are all those values starting at 7. So this is an open circle. This is an open circle at 7, right? It's not filled in. And it's all those things that are less than 7 going this direction. All those values less than 7. And then the last one up there is x's are those things that are less than -4. So again, this is an open circle because we're not at -3, at -4, because we're not including this boundary condition, right? -4 is not a solution, but all those things that are less than -4. Now, it makes more sense now to talk about graphing solutions, because when I graph these solutions, I can see I'm not talking about a single point. I'm not talking about 3 or 7. I'm talking about a whole bunch of points. So the graph kind of quickly shows me where those solutions are. So that's kind of one of the reasons why we like to graph inequalities. And if you were to pop into Desmos and play with it, you would see, oh, it'll graph that, and it's fun to see how it does that. But you can definitely graph these inequalities in it. Okay, so now we get to the point where we're going to talk about, okay, let's solve equations, or let's solve inequalities, right? Let's solve the not equal things. Let's solve some inequalities. And there's a strategy that our textbook outlines, and I like it a lot. There's certainly like things that I end up doing that are kind of more shortcut tricks, and we'll get proficient with those too. But initially, I really want you to think about the solution path that I'm outlining here. So we're going to do basically, I think it's 3 things when we're graphing an inequality. Okay, so this is kind of a first look at what we mean by solving an inequality. I'm asking you to give me all the values of x that make this true. And that becomes kind of problematic, because if you sit here and start thinking, well, I don't know, 15, does that work? Let me try it. What about 20? Does that work? How about -3? Does that work? Don't go there, because trying to grab those numbers and just plug them in and check is I mean, we couldn't identify all of them. So we've got a system here, and here's what our system is. The first thing I want us to do is, and I'm just going to, obviously you don't grab things and move them around like this, but I'm going to set this aside, and instead of thinking about the inequality that I gave you, I'm just going to say, well, let's just make this an equation. We'll just make them equal. And what this is going to do is it's going to allow me to find that boundary point, right? So we're going to identify where our boundary is. So if I distribute the 5, of course, we've got, 10x minus 5 plus 3, which I can simplify to 10x minus 2. And that equals on the other side 8x plus 8. And yeah, I'm just pausing for a second because you're not here to say, oh, Mr. Roberts, that's wrong. So I'm looking, I think we're good. So I'm going to add 2 to both sides. So this left-hand side rather, is going to become just simply 10x. The other side is going to become 8x plus 10. Yeah, that was me adding 2 to both sides. And now I'm going to take away 8 x's from each side, so that's going to become 2x is 10. Therefore, x is the number 5. So I know that everything's going to pivot on this point. This is my boundary location. Okay, that's fabulous. That's your boundary location. But the question I have is, okay, what kind of point do I put at my boundary location? Because remember, we've got options. We can have an open circle, meaning it doesn't include that point, or we can have a filled in circle, meaning that point is part of the solution, right? And it's always this thing right here that tells me if it's going to be filled in. The or equals to says, oh, the boundary is included here. So because this, in fact, I'm going to erase this now. Let me bring the original inequality back into place. Because the original inequality said or equals to, right, I'm going to go ahead and put a solid boundary at 5. So that means that 5 is one of my solutions. It can be 5. Okay, it can be 5. 5 would work. If I put 5 into this top equation, it would work. Then the question is, okay, but which direction do I go? Is it going to be above that or below that? That's interesting. Now, I'm just going to say this right now. You're gonna look at this symbol and you're just gonna guess. Oh, guess what? Listen to what I'm saying. I want you to test a point, okay? I want you to test a point. And the times that you get these wrong, right? When you make a mistake and like, oh, geez, I didn't get the right points. Why is that? It's because you didn't test. So what I mean is that if I'm going to go above it, right? If I'm going to go above this dot, in other words, 6 and 7 are solutions, right? That's one thing. If I'm going to go below it, that's another. I'll just say my favorite point always to test on the number line is the number 0 because arithmetic with it's super easy. So I'm just going to say, well, let's test 0. If it's the case that when I put 0 into the original problem, it works, that means that everything this side is a solution. If it doesn't work, that means it had to go the other direction, right? It's everything over on this side. So putting 0 in here, you can see everything collapses. All of a sudden, this is just going to become 5 plus 3 on this side. And on the other side, it's going to become, if I put in, that's, oh no, it's not 5 plus 3. My bad. I'm putting in 0, right? Zero's okay. Zero's going there. Okay, I'm putting the number 0 in for x. If I put 0 in for that x, that means this is going to become negative 5 plus the number 3. Okay, negative 5 plus the number 3. All right. Well, what is negative 5 plus 3? That looks like the number negative 2. Okay. So I've got negative 2 on this side. On the other side, if I put 0 in for x, I get the number 8. So here's my question. Is negative 2 greater than or equal to 8? Is negative 2 bigger than 8? I don't, No, negative 2 is not bigger than or equal to 8. That means that when I plug in that test value, right, it seems like it's saying this right here, this is a bad spot. This did not work. This did not do what we thought it would do, right? This created a bit of sadness here. And my thing is now that I know that things on the left-hand side of my boundary point aren't working, right? I'm pretty sure it has to be just the points on the right-hand side. Now, I never suggest testing a bunch of these points, right? I don't want you to do it with a lot of them, but this is the first time we're looking at it, so let's test another point. Let's just try. You only need to test the one point. I'm just going to test another one because you're not here to shout at me like, Mr. Roberts, you're doing this wrong. So I'm just going to try another point, and I'm going to put a 1 in for x. So what I'm doing is right now is I'm going to test this. I'm going to test, what if x is 1? What if x is 1? What do we got going on then? Well, if x is 1, the thing in this parentheses is going to become 2 minus 1, which is going to be the number 5. Okay, right? 2 times 1 is 2. 2 minus 1 is 1. 5 times 1 is 5. plus 3. So on this side, I'm going to get the number 8. And on the other side, I'm going to get 8 plus 8. Okay, 8 plus 8. Well, I can see, is 8 greater than 16? No. So you can see, testing that point too, what did we get? We got another, like, no, these points are not doing the thing they're supposed to do, right? So all of a sudden we're rejecting the left-hand side. The left-hand side does not contain our solutions. So where are our solutions? Well, you got it. They're going to be all these things over here, this direction, right? These, and I'll put an arrow showing that it goes on forever. Those are our solutions. So now we can be anything greater than or equal to 5. Now that I'm looking at this graph, this is pretty easy for me to write my solution down, right? X's are those things that are greater than or they are equal to the number 5. They can be 5, 6, 7, etc., right? X's are greater than or equal to 5. So I want to look at two things in Desmos then. So if I was to graph that solution in Desmos, I could say, X's are greater than, let's type right here, X, and then I do the greater than symbol, and then right after I type it, I just hit the equals key, and it turns it into greater than or equal to, and then I'm just going to say the number 5. So what it's done is it's put a nice dot right there on the x-axis at 5, 0, and it's showing me by shading that everything to the right of that's the solution, right? X's are greater than or equal to 5. Now, we're restricting ourselves to just the number line right now, but actually on the Cartesian coordinate plane, any of these points, right? Any of these points, like for example, x is 10, y is 5, that would work because any point where x's are greater than 5 is a solution. So that's right now we're just focusing on the number line, but I want you to know that this solution has consequences for the Cartesian coordinate plane as well. The other thing I want to look at is, let me bring this down here and let's type the original inequality. So if I press enter, I can say, yeah, originally I had 5 times the quantity of 2x minus 1, close parentheses, plus 3, and that was greater than or equal to. Let me do that again in slow motion. So I'm hitting the greater than key and then equals right after it. You can see how it turns it into that. Pretty cool, huh? And then I go 8x and then plus the number 5. Now, 8x plus 8, my bad, plus 8. Okay, so you see what's going on here, right? Now you can see that the answer we found, right, that's just in the red. But if I graph the original problem, right, the original problem, Desmos has looked at it and says, you know what, there's your solutions. It's the same thing. So both of these, if you know how to read the graph, it's saying, x's are greater than or equal to 5. So I point this out because especially as we're away from each other, I want you to have more ways of checking your work and seeing if you're right or wrong. So if you have an inequality like this and you're solving it, right, definitely feel free to grab, especially if you're unsure, feel free to grab Desmo and check your work. But always tie it back to the fact that you have to be proficient algebraically. So, it's a great place to check your work. But remember, the goal is for you to be able to do the work independently. So don't rely on Desmos and its graphs to give you your answer. Just have it be kind of a backstop. So you're just wondering, are you right or you're wrong? And the other thing is, look, you can test several of these values in here, and the more you do that, the more confident you're going to be. One of our teachers on campus, Karen Fifield, is always, Mrs. Fifield always gives the example of, she's a coach, and she says, hey, you can step into the batting cage once, and you can hit that ball, right, solid. And it's just you don't turn around and say, I'm done, right? Look at me, I hit the ball. No, that's just you did it once. But a professional athlete stays in that cage and they keep hitting it again and again and again until they get really proficient. So just because you get a problem right doesn't mean that you're going to be good at doing problems. It means you got a problem right. And if you don't believe me, just watch me play softball. You'll see yeah, Roberts, you just keep swinging and you never hit that ball. Or a better analogy, I've been playing a little of the Call of Duty. What's that game called? The Warzone? What's it? Yeah. My son Evan's here, and I'm terrible. And I'll tell you, they watch me playing, and it's Dad, what's it like? Evan asked me last night. He says, what's it like to not feel like you can tell your hands to do what they have to do with the controller to move around correctly, because it looks like there's, and in fact he's googling like, is there ways to teach old people to play video games, because nope, you're not getting it. You grew up in a time when your controller just had a joystick with just one thing, and now there's like 15 buttons on one of these controllers. So I'm not as bad as I make myself sound, but you know I'm bad. Okay, let's look at one more example before we're done. Okay, so we're going to finish with this one. It is 8 raised to the power of negative 2x plus 1. So that negative 2x plus 1 is all in the exponent. And that has to be less than, that expression has to be less than 1/2 raised to the x minus 18 power. And this is doable, right? Using these techniques where we're going to look at this as an equation. We're going to find that boundary location, then we're going to test to decide if we're going to shade above or below it. It's totally doable. So let's first of all do the tricky part. I'm going to write down this inequality up above here so that we'll remember it was less than. And I'm going to turn it into an equation, and we're just going to find our boundary location. So when we have equations like this, it's an exponential equation. I've got my exponent in the variable. The only trick we have right now is to rewrite it so that the bases are the same. And I'm looking at these two bases of 8 and 1/2, and all I hear is the number 2, right? And I could think about powers of 2, right? 2 to the 0 power, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, and I can go the other way, 2 to the negative 1, 2 to the negative second. And I don't typically have to write these out because I've played with them enough, but I just want us to look at them. First of all, 2 to the 0 power is just 1. This is the number 2. This is 4. This is 8. So we're going to definitely want this 2 to the third. And up here, 2 to the negative 1 is 1/2. So we're going to want this also. So what we're going to do is we're going to replace the 8 and the 1/2 with things that are going to make them look like they have bases of 2, right? They're just 2 raised to some power. So we're going to rewrite this 8 as this is 2 to the third power. But I have to take that number 8 and I have to raise it to the negative 2x plus 1 power. And we're making that equal to. On the other side, we're going to go ahead and write the number 1/2 as 2 to the negative first power, right? Because that is exactly what 1/2 is. And I'm going to raise that to the x minus 18 power. All right, so when I'm looking at this now, I'm going to use the power rule. I'm raising a power to another power, so I'm going to multiply. Again, my thinking here is if I had 3 factors raised to the second power and I raise that to the 5th power, right? I have 5 of these 3 squareds. So I've got 1, 2, 3, 4, 5 of them. So I can see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 factors of 3. So I don't have to write this out. I just have to remember, oh, that is 3 to the 2 times 5, 3 to the 10th power. So I'm multiplying here when I raise a power to a power. So this is going to become 2 raised to the negative 6x plus 3 power, right? Negative 6x plus 3. And that will equal, on the other side, 2 to the, I got to go negative 1 times x, which is negative x, and then negative 1 times negative 18, which is plus 18 power. Okay. What I have now is I have an equation in which the bases on both sides are just the number 2, right? It's 2 raised to power and then 2 raised to this other power. The only time that that's going to be true is if those exponents are equivalent to each other. So we're just going to set these exponents equal. We're going to say, hey, negative 6x plus 3 must be the same as negative x plus 18. And then solving for x, I'm going to add an x to both sides. So this is going to become a negative 5x plus 3. And over here, because I'm adding an x, I no longer have an x. It's negative x plus x is 0. I'm going to take away 3 from both sides, so I get negative 5x equals 15. You can see I subtracted 3 from both sides. And now I'm going to divide both sides by negative 5. So x is negative 3. And, you know, I know a lot of you, observe this a lot. You'll write, oh, minus 2 from both sides, and you'll write that underneath there. I typically don't write that because I like to question myself and say, okay, what did I do? What did I do? What did I do? So when I look from here to here, I can say, well, what did I do? It looks like you added an x to both sides. Okay. What did I, from here to here, what did I do to both sides? Looks like there you took away 3 from both sides. Okay, and I can look at the top line and I can compare it with where I ended up and said, yeah, it does look like I took away 3 from both sides. And then from here, what did I do? So I would like to recommend that you kind of not write all that extra, like, oh, take away 3 from both sides, because a lot of times you'll see that and I just see errors that are made. So I don't know. I suggest just doing the thing and then question yourself, what did I do? And you can write it off to the side here. You know, what did I do? Right here, I added an x. What did I do? I took away 3 from both sides. What did I do? I divided by negative 5. So those are all my properties of equality, right? I'm totally allowed to add the same thing to both sides. I can take away 3 from both sides, and I can divide both sides by negative 5. All right, so now I have my boundary location. I know that this whole thing pivots on x and the number 3. But what I don't know exactly yet is which direction that's going to go. So let's bring a number line in here. And it's safe to say, if you look at the original inequality, it was strictly less than. So I know that it has to be an open boundary. And the open boundary is going to be at negative 3. So I'm going to come in here, and at negative 3, I'm just going to go ahead and put a open circle. I guess I'll do this with this orange pen. Open circle, right? It does not include the negative 3, but that's the center of the universe. Now my question is, do I go above that, or do I go below that? And to answer that question, right, I've identified the boundary, now I need to test. And my favorite test value, if it's available, right, if 0 is not the boundary, I almost always use the boundary to test. We're lucky here, 0 is not the boundary, so we can use 0 as a test value. So let's go back up and look at the original inequality. So in the original inequality, this was not equal to, it was strictly less than. And what I'm going to do is I'm going to put 0 into both sides. So if I put in 0, on this first one, I get, that's gone. So I just get 8 to the first power, which is the number 8. Okay. And on the other side, I've got, and it has to be, I don't know what it is yet, so let me put a question mark here. On the other side, I'm going to put in 0, so it's going to be 1/2 raised to the negative 18th power. Maybe you caught this, maybe you didn't, but a while ago, our book pointed out that if you've got a fraction raised to a negative power, that's equivalent to the reciprocal of that fraction raised to the positive power. Now, fine if you don't remember that, right? You clearly have tools that will let you deal with that. In fact, let me grab our calculator. So I've got a problem with the skin on this calculator is showing things transparent. So I want to evaluate this 2 ways, right? Let's just first of all go ahead and go to the 18th power, right? That's what I'm telling you. If you've got a fraction raised to a negative power, you look at it, inside the parentheses is the fraction, outside to a negative power, I get 262,144. Okay. So let's see if that's the same thing as if I take 1/2. So I'm going to go open parentheses, and I'm going to go 1 divided by 2. That's 1/2. And I'm going to raise that to the, now I'm hitting not the minus button, but the negative symbol down here next to the decimal. So raised to the negative 18 power. And when I press there, it's just like, oh, Ah, you see this? So 1/2 to the negative 18th power really is the same as 2 to the 18th power. So this number is huge. It is 2,000. No, it's 262,144. Well, you know what I have to say? I have to say that is definitely true. Eight is less than 262,144. 8 is definitely less than that. So what that means, if I come back to my graph here, right, it means that 0 worked, right? Put the happy face there. 0 was a solution. And you know what else is going to be a solution? Everything on this side of our boundary point. All of these points are. So that means that it's going to be, it can't be -3, but anything bigger than -3, it could be -1, 0, 1, 2, 3, 4. All of these numbers, forever this direction, are solutions. And if I look at that graph, I can say, oh, you know what that is the graph of? That's the graph of x's are greater than -3, right? All those x values I highlighted were greater than -3. So my solution is x's are larger than -3. Now, I know what you're thinking. A lot of times students will just assume, oh, see this symbol? This was less than in the original problem, right? So therefore, my answer is going to have the less than. I just want to say, please, 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 find the boundary and then test. Find the boundary location and then test. And testing 0 is super easy. Put the 0 in. And if it makes it true, then it's on that side with the 0. If it makes it false, right? If this 0 had been sadness, right? Then all of a sudden I'd be going everything this direction. All right. So guys, that's the video. I hope I see you during office hours. Tell me what you think then. Our homework assignment is going to be the very first assignment in Chapter 9. I'm going to be posting in the classroom today the stamp sheet. And the stamp sheet will have a due date, right? And what I want you to do is just open those stamp sheets up and just go ahead and type in any questions that you have about those problems, right? So open your stamp sheet up and keep referring to that assignment. It'll just be called Chapter 9 homework. You can go back to it daily. Don't submit it, right? Don't submit it to me or turn it in. Just keep opening it up and just type in those boxes, anything that you have questions about. If you're good with a section, you could put a thumbs up icon or a smiley face in the box. But if there's something that's really bothering you, just go ahead and put there. And I'll be looking at those and recording videos to address specific things. So that's it. Good luck today. By the way, guys, I'm always going to try to keep these around 30 to 40 minutes, not longer than that. This seemed a little bit longer today, and I apologize for it. But this is Mr. Roberts. I hope you have a good day. I'll talk to you soon.